White dwarf. A white dwarf is what remains when a star of less than about 8 solar masses runs out of fuel, sheds its outer layers, and leaves behind its exposed core. It is roughly the size of the Earth, but holds up to 1.4 times the mass of the Sun, packed so densely that a single teaspoon of its material would weigh several tons. Nothing inside it is fusing anymore. It is held up not by heat, but by a quantum effect called electron degeneracy pressure, which resists further collapse. With no energy source, it simply radiates its leftover warmth into space, cooling for billions of years. Helium white dwarf. A helium white dwarf is a white dwarf whose core is made of helium that never got the chance to ignite. Normally, a dying star fuses its helium into carbon and oxygen, but if the star is very low in mass, or if a companion in a binary strips away its outer layers early, the core is left as pure unfused helium. These remnants are lighter than ordinary white dwarfs, often less than half the mass of the Sun. On its own, a star small enough to form one this way would take longer than the current age of the universe to die, so nearly every helium white dwarf we see was created by a companion stealing its outer layers. Oxygen-Neon-Magnesium, white dwarf. An oxygen-neon-magnesium white dwarf comes from the heaviest stars that still manage to end as white dwarfs rather than exploding, those around 8 to 10 times the mass of the Sun. Their cores burned hot enough to fuse carbon into oxygen, neon, and magnesium, but stalled before going any further. These are the most massive white dwarfs, sitting close to the 1.4 solar mass limit beyond which no white dwarf can survive. That proximity makes them dangerous. If such a remnant pulls extra matter from a companion and is pushed over the edge, it does not simply explode. Its atoms begin capturing their own electrons, and the whole object collapses into a neutron star. Neutron Star. A neutron star forms when a star between roughly 8 and 25 solar masses collapses and explodes as a supernova, crushing its core far beyond the density of a white dwarf. Protons and electrons are forced together into neutrons, packing more than the mass of the Sun into a sphere only about 20 kilometers across. The density is almost incomprehensible. A sugar cube of neutron star material would weigh as much as all of humanity combined. Its surface gravity is billions of times stronger than Earth's, and an object dropped from a meter up would strike it at millions of kilometers per hour. Pulsar. A pulsar is a neutron star that spins rapidly and beams radiation from its magnetic poles. As it rotates, those beams sweep across space like a lighthouse, and if one happens to point at Earth, we detect a precise repeating pulse. The first was discovered in 1967, and its signal was so regular that its finders briefly labeled it LGM1 for Little Green Men. Some pulsars rotate several times per second. They are among the most accurate natural clocks in the universe, keeping time so reliably that they can be used to detect passing ripples in spacetime itself. Millisecond Pulsar. A millisecond pulsar is an old, dead neutron star that has been brought back to life. When such a star has a companion, it can pull matter from it, and the infalling material spins the neutron star up like a wheel given a push, sometimes to hundreds of rotations per second. The fastest known spins over 700 times every second, its surface moving at a significant fraction of the speed of light. Because they are revived through this process, they are often called recycled pulsars, ancient remnants that have been wound back up into some of the fastest spinning objects in existence. Magnetar. A magnetar is a neutron star with a magnetic field so powerful it defies comprehension, up to 1,000 trillion times stronger than Earth's, making it the most magnetic object known in the universe. That field is strong enough to distort the shape of atoms and to warp the very structure of the vacuum around it. Magnetars occasionally release colossal bursts of energy, and a single flare can outshine the Sun's total output across hundreds of thousands of years in a fraction of a second. The intense field decays relatively quickly, so a neutron star spends only a few thousand years as a magnetar. Stellar mass black hole. When a star of more than about 25 solar masses dies, not even neutron degeneracy can halt the collapse, and its core falls inward, without limit, forming a black hole. Its gravity becomes so extreme that within a boundary called the event horizon, nothing, not even light, can ever escape. Stellar mass black holes typically range from a few to a few dozen times the mass of the Sun, compressed into a region that may be only kilometers across. At the center, according to current physics, lies a singularity, a point where matter is crushed to infinite density and the known laws break down. Black dwarf. A black dwarf is what a white dwarf eventually becomes. Once it has radiated away every last trace of its heat and gone completely dark. It would be a cold, dead, inert sphere of degenerate matter, no longer glowing at any wavelength. No black dwarf exists anywhere in the universe, because the cooling process takes far longer than the current age of the cosmos, on the order of a quadrillion years or more. The universe is only 13.8 billion years old, which means not a single white dwarf has had time to fully fade. Black dwarfs belong entirely to the far future. Thorne-Zytkow Object. A Thorne-Zytkow Object is a stellar remnant hidden inside a living-looking star. It forms when a neutron star, orbiting inside a binary, spirals inward and is swallowed by its giant companion, coming to rest at the star's core. From the outside, it resembles an ordinary red supergiant, but at its heart sits a neutron star, and the unusual nuclear reactions around that buried core produce a distinctive chemical signature. Predicted in 1977, this strange hybrid is one of the few objects that is both a remnant and a star at once. A leading candidate was identified in a neighboring galaxy in 2014. Quark Star. A quark star is a hypothetical remnant that would sit between a neutron star and a black hole. If a collapsing core is pushed just past the density limit of a neutron star, but not quite far enough to form a black hole, its neutrons could dissolve into their constituent quarks, producing a soup of free quark matter, denser than anything a neutron star can hold. Some versions of this matter, called strange matter, might even be more stable than ordinary matter. No quark star has been confirmed, but a handful of neutron stars have measurements that current models struggle to explain. Electroweak Star. An electroweak star is a hypothetical remnant that would form in the brief window when a collapsing core is denser than a quark star but has not yet become a black hole. In its center, the pressure would be extreme enough for the electroweak force to burn quarks directly into lighter particles called leptons, releasing a torrent of energy. That outpouring might be enough to halt the collapse and hold the star up against its own gravity, possibly for millions of years. The energy-generating core could be as small as an apple while powering the entire object. It has never been observed and remains one of the more exotic ideas for how a dying star might briefly cheat its collapse into a black hole. Preon Star. A Preon Star is the most extreme remnant ever theorized, and it may not be possible at all. It rests on the idea that quarks and other elementary particles are themselves made of even smaller components called preons. If that were true, matter could, in principle, be compressed beyond quark density into a preon state, producing an object smaller and denser than a quark star, yet still short of a black hole. Preons remain entirely hypothetical and are not favored by current physics, so the preon star sits at the very edge of speculation, marking the theoretical limit of how dense a remnant could be. Thanks for watching! Which remnant is the hardest to believe is real? Drop it in the comments. Also, please remember to like and subscribe if you enjoyed this video.